lecture. So, as you can see, this is lecture number 9 on the topic of chemical kinetics. Today what we will do is, remember yesterday we were dealing with first order rate equations and the derivation of the integrated rate law of the same and some characteristic features of first order rate equation. What we also introduced was, along with all the general things, was the concept of relaxation time and how the relaxation time can the expression of the same can be obtained from the integrated rate equation. So, today we will move one step further. What we will do is we will have a quick look at second order equations, and so for second order equations everything remains the same, only that it becomes second order. Okay. So, let us talk about then second order reactions, that is reactions that follow second order kinetics. So, we will go back to a general reaction is always like this, A going to P, right, and here we say that the rate R is equal to K A squared. So, once we have this, then what we do is we go ahead and try to derive the rate equation. So, again rate is expressed as minus d of A over d of t. So, we have two sides of the equation. So, one side is this, the expression of rate in terms of the change in concentration, and the other side is this as the rate expression would give in terms of the concentration of A raised to the power 2, this being a second order rate equation. Okay. So, in this case, so what I will do is I will just go ahead and start with this, say this is 1 and this is 2, okay, for this second order reaction. So, now what we do is we equate both sides. So, what we do is we say that okay, now we have this two different expressions for rate, and we say that okay, minus d over d of t is equal to k times A squared, right. So, let this be 3. Again, as usual, as we have done before, we bring A on this side, okay, we take dt to the other side. Now, we integrate. So, within the limits d of A over A squared is equal to minus k dt. So, what are the limits again? Remember, t is equal to 0, then this would be A is 0, when t is equal to t, this would be A t. Okay. So, this A t, remember, as we have been using this term before. Having set this up, you are almost there. So, you just integrate, these are standard integrals. Remember, again on the right hand side you have k, which is a constant, the rate constant, it can be taken out of the integral, right. So, what you are left with is, based on this, what you are left with is, then I have 1 by A t minus 1 by A naught with the negative sign is equal to minus k t, okay, because that is what you are doing. You are doing a standard integral, remember. So, there would be a negative sign. So, there is 2. So, n is equal to minus 2 plus 1 with the negative sign out up front, and then you have the negative sign out here, right, and then this is coming from the integral 1 over concentration of A at time t minus 1 over concentration of A at time 0, or this is the initial concentration, this is equal to minus k t. So, I can cancel the negative signs from both sides, and then I can rewrite this as 1 by A t minus 1 by A naught is equal to k t, or this is the final form 1 by A t is equal to 1 by A naught plus k t, and let this be question number 4. So, this is the final form of the rate equation for a reaction following second order kinetics, based on the fact that you are talking about a single reactant. A single reactant means like this, where A is going to P. A, this is a single reactant, there is no other reactant in place, right. It is not like A plus B, it is only A going to P, and then the rate is given as K times A squared, signifying that it is a second order reaction. Only under those conditions is this equation valid. Now let us try to look at the characteristics of this equation. As you can again realize, see, we mostly try to deal with linear equations, right. So this is also linear equations. We have done it for the 0 order reaction, we have done it for the first order reaction, we are trying to do again the same thing for the second order reaction. So what we see again is a linear equation, there is a linear dependence. So what is the linear dependence of? So you can see, if I go by this equation 4, right, and I say I plot reciprocal of A t, that is 1 by A t against time, I should be getting a straight line with a positive slope. So which means if I have a plot like this with time on the x axis as usual and the reciprocal of the concentration on the y axis, then my plot would go something like this, okay, for a second order equation. And this intercept is what? It is 1 by A naught, and slope is equal to K, right. This is a positive slope, anyway you directly get K from here, okay. So in other words, what we can say is that the signature of a second order reaction is like this, that the plot of 1 by A t, the subscript, that is concentration at different times, against time is linear, right. So the plot of the reciprocal of the concentration versus the time, no matter what the unit is, has to be linear. Only if it is linear, only and only if it is linear, we say that this reaction follows second order kinetics, okay. Good. So what have we done? We started from, when we started from the integrated rate equations, we first introduced half life, right. We will do that the same thing out here for a second order reaction or equation. Then we introduced the 0 order kinetics, we went for the first order kinetics, and we are doing the second order kinetics, right. So let us talk about the half life now. So the half life for a second order reaction. So we are talking about the half life out here. We know now what the half life means again. So T half is what? It is that time at which the initial concentration A naught goes to half of A naught, okay. So that is what T half is. So that is the time taken, for the concentration to fall to half of its original value, right. So if its original value or initial value is A naught, then the time it takes to fall to half of A naught is again T half, as we always keep on saying. So what we will do is, to derive the expression for T naught, we will go back to the expression we had from before, K T. So this was our equation 4. So what are you going to do here? Because it is T half, then what we will do is, this T becomes T half, we will replace it by T half, right, and this A T at T half, what happens is, this is half of A naught. So these are the only two changes we make in the equation, everything else remains the same. You know, that is why, or this is the utility of a rate equation, that you want something you get it from the rate equation, because you have an equation which reflects the dependence of the variation of the concentration on time, right. Okay. So, we will insert these things in equation number 4 to get the expression for T half, right. So, let me write now again. So, then what I said was this is 1 by half A naught minus 1 by A naught. So, I have taken A naught to the other side is equal to K T half, or I can write K T half is equal to 2 over A naught minus 1 over A naught, right, or T half can be written as 1 by K A naught. So, this is the expression for the half life for a second order reaction. What does this T half tell you then? So, what is T half is telling you, it is the time taken to go down to half of its original value, and the expression for T half is given like this. It is equal to 1 by K. K is the rate constant, it is a constant, but it is also dependent upon the concentration, right. That means T half is inversely proportional to the initial concentration or the concentration of the reactant you have in question. So, what does this mean? What it means is, we say that the based on T half is equal to 1 by K A naught. So, this expression we just derived, we say that half life is proportional to the reciprocal. That means 1 by inverse is proportional to the reciprocal of concentration. What does this mean? What it means is, larger the concentration, lesser is the half life. Larger the concentration, lesser is the half life. So, larger the concentration, lesser is the half life. Again, this tells you that this is a feature or a characteristic feature of a reaction following second order kinetics. In other words, the final statement we make about this half life is this. So, you can realize that as my concentration decreases, right, that means as my reaction is proceeding, the concentration of A is decreasing, right, and remember we can have half lives at different times, T half, T14 and so on, and because this concentration is decreasing, what is going to happen, and it is inversely proportional. So, your half life is going to increase, right, because they are inversely proportional. So, what we can say now then is that half life increases as the reaction proceeds, and this is for a second order reaction. In other words, for the second order reaction, as the reaction would proceed, the concentration of the reactant would decrease, and because this half life shows an inverse dependence, that means proportional to the reciprocal of concentration, hence the half life should increase. So, this again reminds you of this fact that T half being a preliminary check of the type of reaction we have at hands. So, let us pause for a moment and think about these T half characteristics. Remember, when we talked about T half, and this was even before we started with the rate equations, we said the T half can give you a guide to what type of reaction you are monitoring, or it can be a possible guide. And then we went ahead, we started with the 0 order. What did we see? The T half was proportional to the concentration. That means, as the concentration would increase, so would T half. Second, we went for the first order. What did we find in first order? We found in first order that T half is equal to natural log of 2 over k or 0.693 over k. T half had no dependence on the concentration whatsoever. So, no matter what the concentration is at any point given point of time in the reaction, T half is always the same. So, that is the signature of the first order reaction or reaction following first order kinetics, and what we just derived was for a second order reaction or a reaction following second order kinetics, then T half is inversely proportional to the concentration, which means that as the reaction proceeds, the concentration decreases and the half life increases. Hopefully now you understand that this T half indeed can be used as a preliminary check for the type of reaction you are monitoring or the type of reaction you want to study or you want to investigate, right. This is the importance of T half or the half life. Now you realize that having done these derivations, it would be easy for you to set up rate equations and derive anything else that you might want to do. Now, if we take a step back and think about what we have derived right now, what we did was this. We said that A going to P. Now, remember for first order kinetics we also did a general equation where A is going to P. That means now the rate is equal to minus 1 by A d of A over d of T, which is equal to k times A squared, isn't it. So, what I want you to do is for a reaction like this which follows second order kinetics, right, derive the integrated rate law, and see how it turns out, where this A, that is the stoichiometric coefficient, is coming in. Okay. Now, another aspect. So, this is one. What did we say? We said that okay, I am still having a single reactant, it is still a single reactant case, A is going to P, that is what we derived right now. Now, I am saying that okay, this A is having a stoichiometric coefficient A, general one, in a general stoichiometric coefficient which might be 1. If A is equal to 1, then I am coming back to this. If A is not equal to 1, say if A is equal to 2, A is equal to 3, whatever, then I have this thing that I have to take care of, right, and that is why you derive the rate law. Now, there is another point to this. The point is that yes, we have done the single reactant case A going to P. What about having two different reactants, for example having A plus B going to P, okay, what will happen there? Now, here, so the rate, this being a second order equation, the rate would be K times the concentration of A times the concentration of B. So, what you are told is that you are given a second order equation, or so this equation follows the second order kinetics, right. It follows this expression, rate is equal to K times concentration of A times concentration of B, both being raised to the power 1. So, 1 plus 1 is equal to 2, and hence this is a second order equation or reaction following second order kinetics. Good. Now, what happens is if concentration of A is equal to concentration of B, right, if concentration of A is equal to concentration of B, then I can rewrite R is equal to K A squared. So, if this is say 6 is 7. Now, once we have this, you realize that this R is equal to K A squared is exactly the same as of having a single reactant, no problem. Now, this is only applicable or only possible when I say that my concentration of A is equal to concentration of B. However, if concentration of A is not equal to concentration of B, that means if concentration of A is not equal to concentration of B, then I can no longer write this. So, my R is always equal to K times A times B. So, then my question to you is, under these conditions where you are given that concentration of A is not equal to concentration of B, you are given that the reaction you are following is of the type A plus B going to P, and that it is a second order equation following this rate expression or rate law. Derive the integrated rate law for a reaction like mentioned above, which means this one, where you are given that the concentration of A is not equal to concentration of B, that A plus B goes to P, and that the reaction is following second order kinetics where R is equal to K times concentration of A times concentration of B. So, this is again another problem for you, please try it out, you will find interesting as to what you get. Okay. Let us talk about a reaction involving several reactants like this. So, let us give it a separate heading. So, this one is a reaction involving several reactants. Okay. Several reactants, right. So, what we mean by this is that we have a general form going to P. So, let this be say 8. So, if this is a reaction, right, where you are seeing that there is a reactant A, there is reactant B, right, there can be other reactants, but we will not make it that complicated. What we say that we will just stick to two types of reactants out here, right, they having their corresponding stoichiometric coefficients which can be 1 or which can be different from 1, right. And we need to establish whether the rate equation can be written as or is of the form R is equal to K is a reactant rate constant, A to the power alpha, B to the power beta. So, this is important. First, this is a reaction involving several reactants, in this case more than one, A and B. Then A and B, they are having their corresponding stoichiometric coefficients small a small b, they are going to P, the products. Now, we are saying that how can we establish whether the rate equation is equal to K times concentration of A to the power alpha, so B to the power beta, where alpha and beta are the orders with respect to those reactants. So, alpha is the order with respect to A, beta is the order with respect to B, and then the total order of the reaction would be alpha plus beta, right. Okay. Now, what is the problem? The problem is this. So, what is the problem? The problem is that the rate of reaction now depends on the concentration of both the reactants, right. So, I can not only look at A, I can not only look at B, because the rate is depending upon both, right. Hence, if this is a problem, what we face with is that it is difficult to separate out the contributions. That means, it is difficult to disentangle it is difficult to disentangle, that means it is difficult to separate out the effect of one reactant from the other. Again what it means is, if the rate is dependent upon both A and B, it is difficult for me to separate out the individual contributions of these two reactants to the total rate, right. So, that is why it says it is difficult to disentangle, but then there are always ways out, there are always ways to tackle problems like this. So, what we then do is we arrange, so way out, what is the way out? So, the way out is we arrange our experimental conditions, in such a way that data analysis will be simplified. Okay. So, what is the way out then? The way out is we devise or design an experiment in such a way that we can simplify the data analysis, right. So, this is the key word, we arrange or design experimental conditions in such a way that the data analysis is not that cumbersome, not that complicated. So, the ways these there are two ways of doing this. So, the two ways are as follows. Number 1, it is referred to as the isolation method, and number 2, it is referred to as the initial rate method. We will look at these two ways separately, and then another feature of these rate equations would come from here. Okay. So, let us take these two individually, you will soon realize why I am going through this, right. It gives you a better feeling of how complicated rate equations can be addressed or analyzed. So, let us talk about this isolation method to start with, right. So, let us go back to our initial reaction. We are talking about this isolation method. Remember the reaction, the general form was A plus B with the corresponding stoichiometric coefficients going to P. Let us take this reaction, which is ClO minus aqueous plus Br minus aqueous going to BrO minus aqueous plus Cl minus aqueous, right. So, now this is a reaction which involves multiple reactants, two reactants ClO minus Br minus, these are the reactants, products mean BrO minus Cl minus. If you remember, I think in lecture number 2 or 3 we had introduced this equation to look at the graphical representations of equations, that means or reactions, that means looking at the kinetic profiles, and this reaction was taken as an example. So, we bring this reaction back and base our forthcoming discussion on this reaction. Okay. So, now having gotten this reaction, so let this reaction, well, let us give it a number, say 9. A plausible rate equation can be written like this. So, we can say a plausible rate equation for this one can be written as R is equal to K ClO minus alpha Br minus beta. So, this is a plausible equation to start with. Let this be 10. Look at this carefully. Let concentration of ClO minus, the initial concentration I mean, that means what you are starting with is 0.1 mole, that means moles per liter. Let the concentration of Br minus be lesser than that, which is 2.0 times 10 to the power minus 3 moles per liter. Okay. So, you set up the reaction conditions such that these are the concentrations of the hypochlorite and bromide that you are starting with. Great. Now, what you soon realize is that this concentration of ClO minus is much greater than the concentration of Br minus. In other words, what we say is that I write in the next page that ClO minus is in excess. Okay. ClO minus is in excess over Br minus. Now, how much excess? Again, that is a very valid point. That is a next logical question you are going to ask. What is the difference, or what is the factor in terms of the concentration difference? So, let us do that. So, then the concentration of ClO minus over Br minus is equal to, if you remember, so this was 0.1 moles per liter and this was 2.0 times 10 to the power minus 3 mole liter inverse. Okay. You do the math, it is very easy, you will see that this ratio comes to 50. What does it say? What it means is, see, it said that ClO minus is in excess. That means ClO minus is in 50 fold excess. Okay. ClO minus is 50 fold in excess than Br minus. Now, let us see what is the effect of this. So, that means you let the reaction run and what you do is you plot kinetic profiles. So, let us now look at the kinetic profiles of the two reactants, being hypochlorite and bromide. So, let us look at the one first for the hypochlorite. So, for the hypochlorite, so what we do is we say that if this is the profile of the reaction, okay, and suppose there are some time points out here, right, this is where I have taken the points. Okay. So, this is for the hypochlorite and what I have on the y axis is the concentration, the molar concentration of hypochlorite. Okay. That is what I have on the y axis. Now, the way I am labeling my y axis, and at least in terms of the numbers, is the following, that I say it is 100 times 10 to the power minus 3. Okay. So, that is 100 times 10 to the minus 3, which is 0.1, and here I say 98 times 10 to the power minus 3. So, what has happened is you are seeing that as the reaction progresses between that of hypochlorite and bromide, this is the change I have for the hypochlorite, and say this observation time is Tn, and say this observation time is Tn. Okay. Now, let us draw the similar kinetic profile, but this time for bromide. Okay. Again, what we have done is we will be taking the same experimental points, right. On the y axis what we have is the concentration of bromide in moles per liter, remember. Now here what I do is I will put in the concentration values. So for example, bromide I start from 2.0, say 10 to the power minus 3, and see where I end at. So this out here say is about this one 0.5 minus 3. Okay. Now what is the significance of the thing or the profile that we have just drawn for the two? So the top one belongs to that of the hypochlorite and the bottom one belongs to that of the bromide. So what are you seeing here? As we saw that the chloride, the hypochlorite was 50-fold excess. So this is what you see out here again. It is 100 times 10 to the minus 3 and 2 times 10 to the minus 3. So it is 50-fold excess. The starting concentration of hypochlorite is 50-fold excess than that of bromide. Now you look at bromide. So from 2 it has come to a very low value, right. Say we are observing it for the same time axis Tn, rather the same time point. So when we are talking about the consumption of the reactants, we stick to this time point Tn, okay, and at Tn, at this Tn we are looking at how much of bromide has been consumed and how much of hypochlorite has been consumed, right. So what do we see? We see for the bromide, it has come down from 2 to very close to 0, right. But look at for the hypochlorite what has happened. For the hypochlorite, for the same time point, it has come down from 100 to a value which is very close to 100, right, just below 98. Okay. We have been consuming the same amount of both because it is related by the stoichiometry of the equation, but something much more important has to be understood out here. What is that? What you will see out here is that the bromide in this case being of limited quantity, it is almost fully consumed. So I can write the bromide ion is almost fully consumed. However, the hypochlorite was in such large excess that we can write the ClO minus is being consumed to a very little extent, and if that is so, we can say then that this concentration of ClO minus with respect to that of bromide, that means with respect to the concentration of bromide, can be treated to be constant, and this is what the subsequent parts of a discussion would rely on or would be dependent upon. That is, when I have one reactant which is many times excess, in this case 50-fold excess than the other reactant. So in this case hypochlorite is 50 times excess than that of bromide, then the bromide is almost fully consumed, but the hypochlorite is consumed to very little extent. So the change is minimal change for hypochlorite, and hence we can say or consider the hypochlorite ion concentration to be constant throughout the course of the reaction, because the change for hypochlorite has been very small, but the change for bromide has been huge, and this is something we always have to think about when we talk about these reactions where one reactant is far more in excess than the other reactant. ClO minus or the concentration, this was in excess, has essentially remained constant throughout the reaction, has essentially remained constant throughout the reaction. Now, if that is so, then what we say is that if the ClO minus has remained constant, then I can say that okay, I can treat ClO minus even at Tn to be almost close or equal to that of its initial value. Why? Because it has not changed at all. So, there is no problem if I make this assumption that the concentration of hypochlorite having not changed that much at all, then is then essentially equal to the concentration I started with, which is the initial concentration, right. So, again based on the kinetic profiles, what you have seen out here is that this bromide concentration has changed significantly, but the concentration of hypochlorite ClO minus has almost not changed at all, very little change. And under these conditions we can say that the concentration of ClO minus has essentially remained constant to the extent that we go ahead and make the approximation that the concentration of ClO minus is approximately equal to the initial concentration we started with. It is not a bad approximation at all. Now, how does this help us? So, you will soon realize how it helps us. So, let us go back to this rate expression. So, the rate expression we started with was this: R is equal to K ClO minus alpha Br minus beta. So, this was 10. Now, this can be replaced as R is equal to K minus alpha. So, I am replacing ClO minus by ClO minus 0 because it has not changed at all. It is approximated to be equal to the initial concentration started with Br minus beta. So, let this be 11, right. Now, once we have made this approximation, once we have changed ClO minus concentration to ClO minus 0, that means initial concentration, then you see what happens is this term is effectively a constant, is not it, because ClO minus initial concentration constant, ClO minus has not changed at all. Approximation is because the change is so little, that is equal to the initial concentration it started with, times K, which is the rate constant, which is obviously a constant. So, I can rewrite this rate equation or this rate expression like this. So, remember I am having this, I can rewrite it as R is equal to K prime Br minus per beta. So, let this be 12, where K prime is equal to what? K times concentration of ClO minus 0 raised to the power alpha. This is question number 13. So, this is the key point. So, you can see that you started with 2 reactants, that means several reactants, in case more than 1, 2. To start with, this was a difficult proposition because we said that we have to disentangle the effects of these 2 as the rate depends upon both. So, how did we disentangle? We said that okay, one of the ways of doing this is to take ClO minus one of the reactants, which in this case is ClO minus, in huge excess. So, 50-fold excess or 50-fold, 50 times rather 50-fold excess or 50 times more than that of Br minus. Once it took that, what we saw is that the ClO minus concentration did not change at all, very little change. Hence, in the rate law, which was the proposed rate law, we said that okay, then the ClO minus concentration is replaced by ClO minus 0, right. It is replaced by this 0 raised to its corresponding order alpha, fine. Having done that, because this is a constant and this K is also a constant, we can immediately replace this by another constant, which is K prime. This is K prime, and this, what is this K prime equal to? K prime is equal to K times the concentration ClO minus initial concentration raised to the power alpha, and in this original equation what we have is R is equal to K prime times Br minus to the power beta. So, what we have done this is this essentially becomes what? This essentially becomes a equation or rate equation depending only on the concentration of Br minus, because the CLO minus is held constant, right. And having said the fact that the rate is now dependent only on Br minus, because this one was in huge excess, we say that the kinetic contribution, now mark these words, having said this we say that kinetic contribution of this Br minus concentration has been isolated. Okay. The kinetic contribution of minus has been isolated. So, that means I have kept the other reactant in so huge excess that now the reaction rate is depending on Br minus exclusively, and that is how you have isolated the effect of Br minus out. That is, you have disentangled, you have separated the effect of Br minus on the reaction rate from that of hypochlorite ClO minus, right. And this is been done how? By keeping ClO minus in large excess. So, only because you have kept the other reactant in large excess have you been able to manage, or have you been able to isolate the reaction such that it depends only on one of the reactants, which in this case is Br minus, because the other reactant was in huge excess. This form of rate expression is something which depends only on the single reactant, as you can see, right, no other reactant. This is what you wanted anyway, because you wanted to disentangle the effects. I keep telling that, separate out the effects, and by doing this you have been able to do exactly what your aim was, or what you started out with, the goal that you had started out with, right. Okay. So, moving forward on this, experimentally now let us move forward and say that, okay, since R is equal to K times Br minus per beta. So, this was 13. Now, experimentally when you do the experiment, say that we observe beta is equal to 1, right. Then we say that R is equal to K. So, this will be prime, sorry, K prime Br minus Br minus raised to the power 1, or R is equal to K prime Br minus. Okay. So, once we have introduced this isolation method, we went ahead and did the experiment, right, and found out that beta is equal to 1, right. Once we found out that beta is equal to 1, we rewrite our rate expression, which is having K prime. Remember, K prime is equal to K times concentration of ClO minus the initial concentration raised to the power alpha times this Br minus, where beta now is known to be 1. So, under these conditions what we say is that this equation we say is a pseudo order equation, right, is a pseudo order equation, and in this case because beta is equal to 1, we say it is a pseudo first order equation. Okay. We say it is a pseudo first order equation. Why? In this case beta is equal to 1. Now, hopefully you will understand where what I aimed, or what I tried to do by introducing the isolation method was, I introduced to you this pseudo order equations or pseudo first order kinetics. And how was this done? It was done by keeping one of the concentrations of the reactants of, or the concentration of one of the reactants in huge excess over the other one. So, that this one did not change, hence the reactant or the reaction rate was uniquely dependent or exclusively dependent upon the other reactant, which in this case is Br minus. So, from two reactants you have kept one reactant in huge excess, so that the rate is depending upon the other reactant exclusively. This is called the method of isolation, and likewise what you have done is it is another pseudo, right, it is a not exactly a first order, but it is a pseudo first order rate constant or a pseudo first order equation, where you have obtained this by keeping the concentration the other one in huge excess. Now, there are many reactions which follow these pseudo order kinetics or pseudo in this case first order kinetics, and they are very common. For example, the acid hydrolysis of ester, right, ethyl acetate is an example of this. What I will do is okay. So, before finishing this up, next class I will take just a couple of examples. So, this was one way of doing it, right. Now, you can understand that, okay, how do we know how it depends upon the hypochlorite. So, in that case what we say is that fine, now I have taken hypochlorite in large excess. Now, the next point is I will take the concentration of bromide in much excess over that of hypochlorite, say again 50 times more. So, under those conditions what will happen is R can be written as K minus alpha, then Br minus beta, but because Br minus is in large excess I can say that this is equal to Br minus 0, the initial concentration. So, then R is equal to K times Br minus 0 beta ClO minus alpha. So, this is now a constant, I can name it as K double prime, hence R would be K double prime ClO minus alpha, okay, and let this be 15. Okay. So, now you did an experiment before where the hypochlorite was in excess, you got the order with respect to bromide. In this case again you do the experiment where the bromide is in huge excess, but you get the hypochlorite, the reaction rate depending upon the hypochlorite exclusively, again you will find in this case that alpha is equal to 1, right. Once you find alpha is equal to 1, then you immediately realize that the rate is equal to K times minus Br minus, and this is what we were aiming for, because the two reactants were reacting together, they were affecting the reaction rate together. What you said was that, okay, I want to separate them out. So, in one case I took one reactant excess, let the reaction rate depend upon the other reactant. In the second trial what I did was I took the second reactant now in excess and allowed the first reactant to define or dictate my reaction rate, and hence get my final rate expression. Okay. So, this is called the isolation method, and by doing the isolation method what we have also introduced you to is pseudo order equations, or pseudo in this case pseudo first order rate equations. Okay. We will do more examples in the next class and then we will move on from there. Okay. Thank you.